Okay, so we'll start off with equivalent circuit once again. Okay, so today's class, recalling equivalent circuit of the transformer. That is the first thing we are going to do. The second thing what we are planning to do is methods of reducing leakage. Then the third thing that we are going to look at is determining the equivalent circuit parameters of the transformer by open circuit and short circuit test. So we'll be looking at those as well. We'll also look at the load test, right? Then we will look at actually voltage regulation and efficiency along with phasor diagrams also, because some phasor diagrams will be needed for the calculation of, the voltage regulation, not for efficiency, but definitely for voltage regulation we will need that, right? So this is the plan for today's class. Right? Okay, so in yesterday's class, we actually said that when we draw the equivalent circuit of a transformer, we are going to first of all consider the resistance of the primary winding, then the leakage reactance of the primary winding as well. The leakage reactance is essentially due to some portion of the magnetic field lines. So we have some portion of the magnetic field lines which are linking only with the primary winding, which we call as primary leakage, and we have some portions of the magnetic field lines which link only with the secondary of the field winding, which we call as the secondary leakage. So we said also that the core is not ideal, due to which we do have some core loss component of resistance. This is a fictitious resistance, not really the core resistance as such. So this is essentially an equivalent resistance that we can, estimate based on how much is the loss that is taking place in the form of hysteresis losses and eddy current losses. And normally this core loss is going to be smaller, because of which if I look at the two portions of the no load current, one which we call as IC, which is corresponding to core loss component of current, right? And one more which we actually take it as the XM, right, which is corresponding to IM. If I may call this as IM, together it makes up for I naught, which is actually the no load current. And this actually, if I look at, this is going to have a very, very bad power factor, because the magnetizing current will dominate over the core loss component of current. The magnetizing current is reactive in nature and the core loss component of current is real, and because core loss component of current is very, very small, invariably the power factor will be pretty bad for a transformer under no load condition. Then we said that on the secondary side we have R2, which is actually the resistance of the secondary winding itself, but we wanted to transfer it over to the primary side, so we call that as R2 dash, where I can write R2 dash equal to R2 multiplied by N1 by N2 the whole square, where R2 is going to be the inherent resistance of the secondary winding, but I want to visualize this from the primary side. So I am multiplying that by the turns ratio square. That's what I am doing. So now that I have transferred, I can definitely connect it together. That's why I was not connecting it together earlier, but now they are electrically connected. There is no problem, right? And then I am going to have X2 dash, which is the leakage reactance of the secondary winding which is transferred over again to the primary side with the help of turns ratio. Now finally, I am going to have a load. And load, if I connect it directly, I would have called that as ZL. Now I am going to call that as ZL dash because I am transferring it over to the primary side again. Right? Let me probably try to give you a little feel for the phasor diagram as well here, because we will be definitely again drawing the phasor diagram in greater detail, but let me try to give a feel for the phasor diagram. So let's say this is my voltage which I am applying for the transformer. So that is the voltage that I am applying on the primary side of the transformer. Now I can draw IC along the voltage axis. Very clearly I am not drawing anything to scale, because of course currents and voltages can be compared in different, they are apples and oranges. I cannot compare them. But when I draw the load current, it is very difficult for me to draw this no load current as 100th or 150th. But so I am just drawing it approximately. That's it, not to scale. So this is IC. Okay. Now I am going to have maybe IM somewhat like this. The magnetizing current is somewhat like this. Now when I add them together, right, IC and IM, I add them together, I am going to get what is known as the no load current. So let me call this as I0. This is what is the no load current. Yes, in the primary side. This is V1. Here I am applying V1. Yes.
So IC will not be in the same phase of V1.
You are right. There is no doubt that IC cannot be exactly in phase with V1 because you have some drop that is taking place in R1 and X1. R1, let us try to look at some of the values. If I am talking about a 2.2 kVA, 220 volts by 110 volts transformer, I told you that the primary current, rated current is about 10 amperes. What I am going to get as the no load current is only 0.2 or 0.3 amperes. And these resistances and reactances, if I look at it in a transformer, the reactance, the leakage reactance will be really small. I can't exaggerate this further. Okay? That is because I don't have any air gap. In a rotating machine, I have air gap. So obviously, there will be huge amount of flux probably leaking into the air gap space. Whereas there is no air gap here, because air gap is very minimal, the leakage will be very small. So the leakage reactance typically of a transformer will be, if I look at in terms of voltage drop, the voltage drop will be only about 2% or 3%, nothing more than that. Totally put together, the voltage drop in R1 and X1 as well as R2 dash and X2 dash put together will be only less than 5%. That is under full load current condition. 10 amperes when it is flowing for a 2.2 kVA transformer, out of 220 volts, if I try to find out how much is the drop that is taking place in R1 plus R2 dash plus J into X1 plus X2 dash multiplied by the 10 amperes will give me a drop of only about less than 11 volts, 10 volts or 9 volts or something. It's going to be so low. That is the case even when full load current is flowing. So if lesser current is flowing, which is 2% of the current, who cares really? So the drop is really small during no load condition. So I can very happily neglect the drop across R1 and X1. I can say that V1 and E1, if I may call this as E1, capital E1. So I can say V1 is equal to E1 under no load condition. That is the reason why I couldn't care less in terms of whatever is the phase shift that may exist between IC and V1. It's hardly anything. So I'm just taking that both of them are in phase. Now I have this as the no load current. Got it? Once I got this as the no load current, let's say I have connected the load now. When I connect the load, I'm going to have definitely a secondary current. So the secondary current, let me call that as probably I2 dash. I should not call that as I2 because I have transferred it over to the primary side. So I can't call it as I2 anymore. I have to call it as I2 dash. So I will have some I2 dash, and I2 dash phase angle depends upon what kind of load I have connected. If I have connected highly inductive load, I'm going to have I2 dash probably lagging behind V1 or E1 for that matter by a very, very large angle. If I am connecting a unity power factor load, the current will be along IC itself. If I am assuming that I am probably connecting some kind of lagging power factor load, I should in fact show it much longer than what I have shown, because the load current will be very, very high as compared to the no load current. The no load current is only less than 5%, then I should show the length of this particular current I2 dash as almost 20 times or 25 times whatever is my no load current, which right now I am not able to show. So I am assuming that you guys understand basically the constraints. That's the reason I have shown this as the load current. So this is going to be actually my load current. This is the load current. If I have the load current here, then I can add this current, which is actually my I0, and this is I2 dash. These two added together will make up for I1. So I should say I1 vectorially is equal to I0 plus I2 dash. And I0 is actually equal to Im, right? That should be Jim minus Jim, right? Plus IC. That is what is I0 actually, because it is lagging behind, right? So I should say IC minus Jim is the overall no load current, and no load current added to I2 dash. That is what is going to give me the total primary current. Am I right? Okay. So now I should be able to draw finally the overall current, right? So I should actually draw I0, which is probably, I will show it like this. I hope so that I am showing it in the correct angle. So this is I0. So now both of them added together, I should have this as I1. This is the overall I1. So if I draw the power factor, actually speaking, the load current power factor, I have taken that as the angle between V1 and I2 dash, which is not accurate. I should take it as V2 dash and I2. I have to look at what is V2 dash. V2 dash is what is available here. This is V2 dash. I hope you understand. This should be V2 dash. So I have several drops. First I am applying V1. Minus R1 plus JX1 multiplied by I1 will give me E1. So this E1 is going to be now passed on to the secondary side, which I may call that as E2 if I am not taking the turns ratio into account. But if I am taking the turns ratio into account, E1 and E2 dash are the same. They are one and the same because they are following the turns ratio. Now E2 dash will be passed on to the load after getting dropped in this R2 and X2 dash. So I should say E2 dash minus I2 times R2 plus R2 dash plus JX2 dash. So I should be able to write this, saying that V1 minus I1 plus I1 multiplied by R1 plus JX1. This will be E1. which is also equal to E2 dash. Right? But I should also write E2 dash minus I2 dash multiplied by R2 dash plus JX2 dash is equal to V2 dash. Are you getting my point? So there are two drops clearly, voltage drops. We are considering mainly the series portion because that is where the voltage is dropped. Right? So if I draw the power factor, approximately I can say maybe this is the power factor of the load. But that is approximation because I have taken directly the angle between V1 and I2 dash. Actually I should have taken V2 dash and I2 dash. Okay? But the saving grace is R2 dash plus JX2 dash is very, very small. Because of which, although there is a drop, I can say, theek hai, these two are in phase with each other. That's fine. Definitely there is a phase angle. So let us probably try to account for it. Okay? So, if I have, let me say probably V2 dash is somewhere here. I'm just going to arbitrarily draw V2 dash. It's not really exactly correct. Maybe this is V2 dash. The length should not be so much. Right? Okay. So it will erase the whole thing or it will not erase at all. Okay. Fine. So this is what is V2 dash. Fine. This V2 dash, to that I have to add what? First of all, I2 dash multiplied by, exactly. No load is open circuit. No load and open circuit are synonymous with each other. They are synonymous with each other. Okay. So, to V2 dash, I have to add first of all I2 dash multiplied by R2 dash plus JX2 dash. That is the first thing I have to do. Then I have to add I1 multiplied by R1 plus JX1. If I add both of them, then I should get V1. Am I right? So, rather than doing that, let me assume, although I have written all these fully, I can say I1 is approximately equal to I2 dash. No harm in writing that. After all, because the no load current is really, really small. So, as an approximation, what I am going to do is, to V2 dash, I am going to add first of all I2 dash times R1 plus R2 dash directly. So, this is I2 dash. So, I can write this as maybe I2 dash multiplied by R equivalent, where R equivalent is R1 plus R2 dash. Okay. So, I am going to have essentially R equivalent equal to R1 plus R2 dash. Similarly, X equivalent is going to be X1 plus X2 dash. Right? Overall series resistance of the transformer and overall series reactance of the transformer. Am I right? So, I can take it like that. So, what I am doing is, to V2 dash, I am adding first of all the drop in the resistances, two resistances. So, I am going to take the drop in R1, take the drop in R2 dash. That I am going to multiply by the resistance. And after all, the current multiplied by resistance will be in phase with the current itself. Right? So, I have taken this in phase with this. These two are in phase. And to this, I have to actually draw a perpendicular. So, I have to take it like this. If I drop a perpendicular, that perpendicular is indicating that the resistance drop and inductance drop will be at right angles to each other. I hope you understand. The current and the resistance drop will be in phase with each other. And the current and the inductive drop will be perpendicular to each other. So, once I write this as I2 dash multiplied by X equivalent. then I have to just extend this and then say this is what is V1. This entire red line is V1, not the original blue line. This entire red line is V1, right? Okay? So, I can draw the phasor diagram indicating separately R1 and R2 dash drop and X1 and X2 dash drop. Rather than that, I have put both of them together so that I look at the overall terminal voltage vis-a-vis whatever is the voltage that is applied from the primary side. So that's what I have taken as the overall, the drop that takes place within the transformer. So let me again recall the phasor diagram step by step because I have made a little bit of modification here and there. First of all, we drew a voltage which is the applied voltage, V1. From there, we first drew the no load current. So the no load current has two components. One is core loss component of current which is in phase with the voltage. The other one is the magnetizing current which is at 90 degrees. Although it doesn't look like 90 degrees in the figure I have drawn, but it should be exactly at 90 degrees. When we add these two, we are getting the no load current. So I0 is the no load current. Where we are adding Im and Ic, both of them. So I0 is the no load current. Once I get I0, my no load phasor diagram is done almost. After that, I have to include the load or take the load into account. The load current that is flowing is I2 dash. Okay? Actual load current flowing is I2. I have taken it with the help of turns ratio to the primary side and I am calling that as I2 dash. Now, this I2 dash and I0 added together will give me I1. So, I should have taken into consideration when I take the drop through R2 and X2 dash, only I2 dash. Whereas, when I take the drop in R1 and X1, I should have taken I1, which will include the no load current as well. But the no load current is only less than 5% of the full load current. So, it's okay if I neglect it. So, I am taking as an approximation I1 equal to I2 dash. So, now what I am doing is I1 or I2 dash I take into consideration and I take all the drops that are taking place in the series parameters like R1, R2 dash, X1, X2 dash. So, R1 plus R2 dash I am calling as R equivalent and the drop in that R equivalent will be in phase with the current. So, what I have as the current, I can just take parallel to that I2 dash times R equivalent. And then perpendicular to that will be X equivalent drop. So, I have taken I2 dash times X equivalent. When I add these two, actually I can drop a vector here which is I2 dash times Z equivalent, if I may call it as that. So, I could have drawn a vector here which will actually show me as I2 dash times Z equivalent. If I feel like, I can show it. Now, V2 dash plus whatever is the drop that has taken place in the impedances within the transformer, series impedances within the transformer, these two added together gives rise to V1. Right? So, that is what is actually my V1. So, if you actually look at it in a transformer, between V1 and V2 dash, the phase angle will be really, really small, normally. Right? So, that is the reason it's alright sometimes to start off the phasor diagram assuming that V1 and V2 dash are at the same phase and you start drawing the phasor diagram and then when you get more parameters, you try to make small little amendments. That's what we do. Right? Is this clear? The phasor diagram of the transformer, is this clear? Any questions on this? Yes. It can't be completely inductive. It will be resistive plus inductive. But it will be reactive, yes. It is not at 90 degrees. No. See, please remember that this is voltage, whereas this is current, I2 dash or I1. These are currents. Current should lag behind the voltage, which is happening. Look at them individually. This is, okay, let me probably draw this portion, slightly expanded here. This was my I2, right? What I drew as I2 dash times R2, let us say I draw like this. I2 dash times X2 is like this. So this is I2 dash R. This is I2 dash X. Of course equivalent. Okay? Now when I look at this, this is I2 dash Z equivalent. Now look at the phase angle between this and the current. Don't you get that now? The current is lagging. That's what it is. Right? I hope I have made myself clear. Yeah. Yes. We are neglecting when finally we drew the voltage drop. We didn't neglect it initially. That's why we wrote very clearly IC, IM, sum of that is no load current. Then that no load current we added to I2 dash and we said that was I1. But finally when I was writing the drop, I could have written I1 times R1, I1 times X1 plus I2 times R2, I2 times X2. All these things added together will give me the total voltage drop. But it is actually hair splitting. You don't really need so much of hair splitting. So we will try to work out maybe one problem at least, right from the parameter estimation of a transformer until voltage regulation and efficiency calculation. So that will give you a feel for what kind of values we are getting. If we neglect it, heavens are not falling. That's what it means, right? So engineering approximations are always done so that finally what you obtain as experimental values somewhat coincide with the actual calculated values, then you say your assumptions are okay. That's all, right? So we are not going to do as accurate calculations as a mathematician does. Definitely not, right? Okay. So having said that, now we have to go and take a look at first of all whether we would be able to get these values, that is R1, R2 dash, X1 and X2 dash, and similarly the values of RC and XM at least to a good accurate extent, that is acceptable accuracy, whether we will be able to get them experimentally. That is one thing we'll have to do. Second thing, we also know now that the voltage drops that are taking place in R1, R2 dash, X1, X2 dash are uncalled for. But we have to live with them. Can we minimize them? So these are two questions that we are going to answer in the next few minutes. Okay? So first thing is whether we can decrease, can we reduce the voltage, the series voltage drops? That is the first question that we are going to answer. If we want to reduce the voltage drop, R1 and R2 dash first of all have to be decreased. The maximum we can do is to use a material which is of very, very low resistivity. That's why we normally use copper coils, although copper is more expensive. Most of the transformers use only copper coils, right? But sometimes when we buy it from the grey market, what they do is already used copper in any old motor or something, they take it out, just beat it up again so that it looks good copper, it looks like good copper, and then they put it up, and invariably we find that the transformer fails within a few days. So generally, at least in the laboratory when we buy, we make sure that we test it properly, all the parameters of the transformer, and only when we know it is fairly good, we release the payment. That's what we do. And we try to order it from fairly renowned industries, right? So this resistance being low is important to make sure that the performance index of the transformer, like efficiency and voltage regulation, that is the voltage drop, should be contained within a particular limit. So these things should be done. So resistance, yes.
Ma'am, what happens with copper if you use that?
If you use it, see, basically it gets oxidized, definitely. And when it gets oxidized, unless you remove the oxidation portion, the resistance will not decrease. What these people do is,
Ma'am, current is flowing inside the copper, not on the upper surface.
everywhere you are taking into account when you actually choose a wire for a particular gauge thickness, you are going to assume that the entire cross-sectional area is occupied by the current. So if the outer shell is not occupied by the current because it is highly resistive, then you are overheating the inner core, which is not good, right? So generally it is not, it is not a good idea to choose a wire whose thickness is less than what you anticipate as the current limit. So generally you go with the consideration that you will give a factor of safety of 1.25 or 1.5. So if I expect that 15 amperes of current has to flow through my copper coil, I would say what is the amount of current density the copper can withstand, and I will put generally 1.5 times 15 as the factor of safety, and then I will choose correspondingly, depending upon the current density, what is the area of cross section I have to choose for the wire. That is how we choose. Okay, so first of all, R1 and R2 dash should be as low as possible. So this will be ensured by choosing a good quality copper wire, normally. The second thing we would like to do is very clearly to reduce the leakage. So to reduce the leakage flux, what we are going to do normally is to put the primary and secondary as much as possible sandwiched in the same limb. So if I say that this is what is the transformer's core, right? I may put actually primary here. Let us say this is the primary coil. Then I may put the secondary coil right beneath that. Again I will put the primary here. Then I will put the secondary once again here. Similarly, I will put it on the next limb also. So I am going to have the primary and secondary, secondary sandwiched continuously, and of course I have to connect these two in series. I will have to connect these two in series. Similarly, I have to connect these two in series. So I have to necessarily connect them, no doubt, because all the turns have to come in series. Only then I am going to get n times voltage per turn equal to the overall voltage. So I have to connect them in series. But I will have essentially primary and secondary sandwiched in one particular limb itself, and the next limb also, yes. We can do that also, that's another way. Concentric coils, we call them as concentric coils. So this is in case both of them are of comparable voltage. If both primary and secondary are of comparable voltage, the comparable voltage thing will come up when I want only isolation to be established. Maybe I have a 220 volt system, another 220 volt system. I don't want the earths to be coming together. So I will have one primary 220 volts, one secondary 220 volts. From the primary I may supply the voltage, from the secondary side I may connect it to some motor or load or rectifier or whatever. So I want isolation very clearly between the primary and secondary, in which case they will be of the same voltage rating. So I can put them like this. Whereas, so I would call this as sandwiched This is sandwiched coil. Sandwiched coil. Whereas I may have something called concentric coil. Concentric coil is what just now Swayam told. So I will have probably my primary here. It is wound around the limb. And the secondary is going to be probably around that as well. So I am showing something like a cross section or longitudinal section. Are you getting my point? So if I say that this is my core, right? I am going to have one coil like this. So this is all occupied by the coil, let us say. Right? This may be primary. And I will have the secondary around this. So this is actually my primary coil probably, and this is going to be the secondary coil, and this is going to be the core. Right? So this is what is concentric coil. Yes? It can be in square shape, it can be in circular shape, it depends upon how the laminations you have designed. Right? It depends upon very clearly the laminations you have designed, because if I have all the laminations of the same shape and same size, then it is going to be square. If rather than that I am progressively reducing the overall thickness or overall width, then it will look as though it is triangular, or it can approximate itself to something like I can have it this way basically. So I can have something like this. I am just showing approximately. So similarly the other side also it can go like this. So I can approximate it to a circle. I can do this also. So it depends. It depends. Right? Now, please note that the core is also conductive, or it is metallic. Right? And the primary and secondary coils, definitely they are made up of copper. They are also conductive. We will put insulation around them, no doubt. If the primary is of low voltage rating, then I will put primary inside and secondary outside. Because if the secondary is of 400 kV and the primary is of 15 kV, 15 kV will require only less insulation. Whereas 400 kV will require thicker insulation. And because I require thicker insulation, very clearly the coil turns will probably be of higher diameter. Because it will be really thick, it will be very difficult to wind it into a smaller diameter coil. So one thing is, because of the inherent diameter I will get for the coil, as the voltage rating increases, I will have thicker insulation. So the diameter of the coil will become larger and larger. Whereas one more reason is, because the core is also metallic, I need to make sure that the breakdown strength of the insulation is good enough to withstand the voltage, the coil making a puncture onto the insulation and reaching out for the current into the core. So the core and the coil are separated only by the insulation. If the voltage, the strength, whatever dV by dt if I am talking about, or dV by dx, where the centimeter I am talking about the thickness of the insulation. If that exceeds the insulation strength, then the insulation will be punctured. Higher the voltage, I will require higher as the separation distance. So if it is lower voltage rating, I can put it closer to the core. Whereas if it is larger voltage rating, I better put it away from the core. So larger voltage rated winding will be placed in the outer concentric circle, whereas lower voltage rated coil will be placed in the inner concentric circle. So this is one of the ways of decreasing again leakage reactance. So sandwich coil and concentric coils. These are two ways of reducing leakage reactance. One more generally that is done is we never make the core broader and thicker. We try to make them thinner and longer. Like this. I'm sorry for the bad drawing. Okay. This is how we make it so that the air path really becomes longer. This is the air path. This is, if I am saying that a flux is having a path like this, it is going through the window. So we call this as the window. And these are limbs. Right? Limbs of the core and window of the core. The window is generally made, thinner and longer. That makes essentially the length of the air gap path, really increase. If the length increases, we said L by mu A is the overall reluctance. So the reluctance is going to increase further and further. If the reluctance increases further and further, the number of lines that are escaping into the air gap will decrease. If the number of lines escaping into air gap decreases, the leakage decreases. Right? The total number of lines that are confining themselves to the core will be increased correspondingly. Right? So, three ways of reducing the leakages. One is to increase the length of the window. The second is to have sandwich coil. The third one is to have concentric coil. And the fourth one is shell type construction. We looked at shell type and core type. Core type construction always enhances air, surrounding air more, where it makes it more. Whereas in shell type construction, mostly it is surrounded by iron. So hardly anything escapes into air. So shell type construction generally enhances or reduces the leakage quite a bit. So these are four ways of reducing, the leakage in the case of a transformer. Fine? Now that we have seen the importance of R1, R2 dash reduction and X1, X2 dash reduction, let's try to see how to estimate the parameters or equivalent circuit parameters of the transformer. Okay, so let us try to look at two tests that are commonly conducted in a transformer to ascertain the equivalent circuit parameters of the transformer. So, one of them is open circuit test or no load test. The other one is short circuit test. Rather than doing this, we could have simply loaded the transformer. Let us say I have a 2.2 kVA, 220, again let us take the same parameter what we had taken, 220 by 110 volts transformer. Right? If I have to conduct a test on this transformer and ascertain when I load it to the fullest extent how the transformer is really performing, that will give me a clear picture of how it is behaving when I load it to the fullest extent, or when I load it with inductive load, when I load it with capacitive load. I can definitely conduct the test. But the transformers normally we use in the power stations or industries, they are all of the rating of thousands of MVA or at least hundreds of MVA. For example, what we use in a power station which is generating 400 MVA power, it will be 400 MVA transformer with probably 15 kV or 20 kV whatever slash maybe 400 kV. This is the kind of thing that we are going to see in a power station. And if I have to test this transformer directly by loading it, it will be really a monumental task. First of all, how will I find the load which will carry whatever is 400 MVA divided by 400 kV. That much of current. So I have to essentially get a load which will actually carry so much of current and it will dissipate so much of power. Then I should be able to cool it, right? It's not a joke. So it is going to be really difficult for me to test such a transformer by loading it actually, and it will be a huge wastage of power. So rather than doing that, if I can do something like create, such kind of condition which will be equivalent to loading it fully without actually loading it. And that's what we do in these two tests. In open circuit test and short circuit test, we are essentially creating situations such that the transformer is put through such an operating condition which will emulate the normal loading condition, although not simultaneously. What I mean is, in open circuit test, you will apply rated voltage but lower current. And in the other test, which is short circuit test, you will apply rated current but lower voltage. This is what we do in these two tests. Yeah. V1, because E1 is internal to the transformer, which we cannot measure. And after all, the difference between V1 and E1 is not too much. Chalega. That's the reason. Okay? So we always go by engineering approximation. Again, that's the reason. So if we subject it to 220 volts on the primary side or 110 volts on the secondary side, I call that as rated voltage. It is being subjected to rated voltage. Right? Similarly, if we pass 20 ampere on the secondary side or 10 ampere from the primary side, I call it as the transformer is being subjected to rated current. And that's what we do during short circuit test and open circuit test respectively. Okay? So in open circuit test, as the name indicates, we are going to keep the secondary open. So let us say this is my transformer. Right? And then I am going to keep this open circuited. And here is my core. And invariably, the open circuited portion will correspond to high voltage side. The open circuited winding will be HV winding, whereas this will be LV winding. LV corresponds to low voltage winding, the other one is high voltage winding. So if I am having, instead of 220 by 110, if I think of 22 kV divided by 110 volts, even it can be like that. If it is that way, then invariably I will try to apply 110 volts because that kind of source is easily available for me. 22 kV will be difficult for me to get. So always I will try to choose the low voltage winding to be energized in the case of, the open circuit test, because I am looking at applying rated voltage. So the rated voltage has to be corresponding to either low voltage or high voltage, but logistically it will be easy for me to apply the voltage on the low voltage side rather than high voltage side, because high voltages are not common. High voltage sources are not common. Right? So now what I am going to do is to apply. So normally what we do in the laboratory is to apply it through a variac or auto transformer. We will study about auto transformer a little bit later. But let us say I am having this as single phase 220 volts 50 hertz AC. This is what is available. Now I am going to connect this to something called as an auto transformer. Auto transformer is like an inductor, iron core inductor, nothing else. I just have a larger number of coils okay, that is wound in an iron core. Now I am applying this entire voltage to that coil. Now if I tap only 4 number of turns, I will get only half the voltage, half the number of turns. If I tap the 100% number of turns, I will get complete voltage. If I choose only 75% of turns, I will get only 75% voltage. It's as good as a potential divider, but without resistive loss. That's all. I don't have any resistive loss. And it works because of highly inductive nature of this iron cored coil. Right? So from here, I'm going to apply this voltage to the low voltage winding through an ammeter and through a wattmeter. Okay? So this wattmeter is connected in between the primary coil and the input source. Right? Now, please note that there is no current flowing on the secondary side. So I2 is 0. So what I am having as I1 here will be equal to I0. That is actually the no load current itself, nothing more than that. So what I am getting in the open circuit test is only no load current. And as we know, the no load current of a transformer is really small because of the no load losses being decreased and also the permeability of the core being very high. So I can say that even if I consider the series resistance of the transformer, which I may say R1 and X1, the series resistance loss is going to be really small. Let's take the quantities. If I say that at 100% load, I am going to have I1 square R1 to be 100 watts, let's say. Then I am having only, 5% of the current or 2% of the current flowing. The current is going to be only 0.02 times I1, for example. And I have to see what is the loss at this condition. It will be 0.02 I1 square times R1. This will be the no load condition series resistance loss. Right? So if I try to look at this is 0.0004, which means it is less than, not even 4%, it's 0.04%. 0.04% of what I would have incurred in R1 as the loss under full load condition. So originally if it was 100 watts, now I will have only 0.04 watts as the loss. Am I right? Which means it is going to be really small, so I can afford to neglect it. So under no load condition, we take it that the series parameters hardly ever play a role in the voltage drop as well as in the power loss. So the series parameter that we can even consider is R1 and X1, because R2 and X2 don't even have any role to play. It's not even carrying any current. So R1 and X1, both of them hardly play a role because of the fact that I am not going to have a good amount of current flowing through the transformer under open circuit or no load condition. Right? So I can say in general that in open circuit test, what we get as the wattmeter reading. So if I may call this as W0, W0 will be basically only the core losses. It will not contribute to anything towards copper loss. Think about it again. I am applying rated voltage at rated frequency. So the flux will be at rated value. Are you getting my point? E equal to 4.44 F phi m into number of turns. This is what we wrote as the equation. So if I am talking about E1 This is N1. So if I look at the flux value, if I am applying rated voltage, whether it is from the primary side or secondary side, it doesn't matter. The flux is going to be at rated value as long as the frequency and voltage are at rated value. So if it is at rated value, then I am essentially looking at the overall magnetic circuit depicting a behavior which is very similar to nominal operating condition. So under normal operating condition, however the magnetic circuit may be, that is what is the behavior depicted by the transformer under this condition. So if the flux is at rated value, the frequency is at rated value, the voltage is at rated value, I can say the core losses will be at rated value. Whereas the copper losses are very, very minimal. So whatever is the reading I am getting from the wattmeter, I would call that as the rated core loss or no load loss. The core loss incidentally is also called as iron loss, and they may also be called as copper loss, constant loss. Constant loss we call it because we assume that if the transformer is rated for 50 Hertz and 400 volts, it will always be operated at 400 volts and 50 Hertz. Hardly ever we operate it at lower voltage, hardly ever we operate it at a different frequency than what it is rated for. So we assume that as long as the voltage and frequency are kept as a constant, the iron losses or core losses are constant, so we call them as constant losses. So it's called as constant loss because the voltage and frequency will be normally maintained as constant. That's the only reason. Right? So what we get out of the no load test is we are going to get W0, V0 and I0. These are the three readings that we are going to get. V0 invariably will be rated value. I0 will be probably less than 5% of I rated if it is a well designed transformer, and this is going to be core losses. Right? So I should be able to get rest of the equivalent circuit parameters in the parallel circuit, because the parallel circuit is the one which is talking so much about magnetism, the parallel portion of the equivalent circuit. So I should be able to say W0 equal to V0 I0 cos phi naught. So cos phi naught can be deduced. Right? Once I have cos phi naught, I should be able to say, see, we drew the phasor diagram, if you may recall. If this is V, I'm going to have IC along this and I'm going to have IM along this. So the resultant current what I get will be somewhere here, which is corresponding to I0. And if I may say, this is what is phi naught. This is phi naught. Right? If this is phi naught, I should be able to say that I0 times cos phi naught will be IC and I0 times sin phi naught will be IM. Right? Once I get this, I can say simply V0 divided by IM will be XM. Right? Because they are in parallel. So I should be able to say V0 by IC is RC and V0 by IM is XM. Had it been an ideal transformer, what would be the value of IC, RC and XM? If it had been an ideal transformer, how much will be XM? Infinity or 0? Sure? Infinity? It has to be infinity because Im has to be 0. I should be able to establish the flux without any current. If the permeability is infinity, without any MMF, I should be able to establish flux within the core. So, for an ideal transformer, these two should be infinity. Because I will not have any IC, I will not have any IM, I should not have any core losses, I should not have any requirement for the current for establishing the flux. Right? Okay? So, we will, yeah. RC, if RC is 0, IC will be infinity. So, if IC is infinity, the no load current of the transformer will get to infinity. In a transformer, if I am not connecting any load, if it is an ideal transformer, the no load current should be 0. Got it? So, I can't have RC to be 0 either. What you say is right. If RC is 0 or IC is 0, I should get core losses to be 0. But, although that is true, if I have RC to be 0, the no load current will literally become infinity. They are in parallel. Remember that. RC and XM are in parallel. So, if RC is 0, I will have no load current reaching infinity, which will not be the case, which should not be the case. Got it?